Do you want me to keep my camera on whilst I'm doing the presentation, or shall I switch it off?
It's up to you. You may switch off also, no problem.
You tell me, in case it takes part of the screen, you know, it may not be visible. So just tell me I can switch it off so that people can concentrate on the presentation rather than seeing my face.
Yeah, you may keep it switch off, no problem. No
yeah,
problem.
okay.
Good morning, Professor Mousha.
Hello, good morning. How are you? Are you okay? Hello, Professor.
Good morning, Professor
Good morning.
Good
How
morning.
Are you? Are you okay? Yes. Good morning.
Morning.
So we'll start. So good afternoon, all the participants and my co-organizer and the expert members, both Professor Ghanim and also welcome to Professor Mousa. So today, this is our last session of this course, and the title of presentation is Integration of Renewable Energy and Electric Vehicle in Microgrid, and it will be presented by Professor Ghanimpotros, Northumbria University, Newcastle upon Tyne, UK. Regarding brief bio of Professor Ghanimpotros, Putrus is Professor of Electrical Power Engineering at the Department of Mathematics, Physics and Electrical Engineering, Northumbria University, UK. He has over 30 years of research experience with over 200 publications, including 1 patent, and has given several invited talks at national and international events. He has led several research projects and had often provided consultancy for industry. He has led several research projects on the integration of renewable energy generation and electric transport into the electricity grid. Professor Putrus is Associate Editor for Elsevier Renewable Energy Journal and serves on the editorial board for the World Electric Vehicle Journal and the technical steering committees for several conferences. He is actively involved in the Institution of Engineering Technology, Chairman of the IIT Northumbria Network 2004-5, and served on the Executive Committee for the Power Trading and Control Professional Network 2001 to 2010. His main research interests are application of power electronics in power system, integration of electric vehicles, and renewable energy sources into distribution networks and smart grids. So now I request Professor Ghanim to start his presentation.
Thank you.
Thank you.
Thank you, Professor Provat, and thank you, Professor Arnab, for inviting me and for the introduction. I'll share my screen now.
Yes.
You see my presentation?
Yes, sir, it is visible.
Yeah,
sir.
Good. Yeah, I think before I start, if you don't mind, I'll switch off my camera also so that you can concentrate on my presentation rather than my
Yes, no.
Yes.
Okay. Can you see it?
Yes, sir.
Yes,
Yeah,
yes.
Well, as Professor Provat said, my name is Ghanimpotros. I'm Professor of Electrical Power Engineering at Northumbria University, and I'm going to talk today about integration of renewable energy and electric vehicles in microgrids. Before I start, I just want to acknowledge all the work that many people worked with me over the years and contributed in one way or another to this project. I would like also to acknowledge the funding we received from the British Council and the Department of Science and Technology in India through the UK IERI, which is the UK India Education and Research Initiative. They funded a project for us, which we are working with, and I'll explain a little bit about it later. And with this project, really, these webinars we are doing with IIT Goa and NIT ROURKELA, and likewise they are doing webinars here at Northumbria. So thanks to all for their contributions. The presentation, I'll give a little bit of introduction, and then I'll look into the impact of renewable energy, and then the impact of electric vehicles, and then look into the synergies between the two and see if there are any opportunities if we integrate these two together. And then look into microgrids, energy autonomy, control, optimization, and then finish with a summary. Before I start, I just thought we'll give you a little bit introduction about Northumbria University, where I work. Northumbria University is in Newcastle upon Tyne, which is northeast of England. It's about 280 miles from London. London is here at the bottom, and Newcastle is here northeast. We have 4 faculties at the university. Faculty of Engineering and Environment, where I work, and I work within the Department of Mathematics, Physics, and Electrical Engineering. We have several research groups in the department. I work within the Electrical Power and Control Systems Research Group. And those of you who are still doubting where Newcastle is, you probably remember Newcastle United, the football club, which is not doing that well this season. Recent projects I have been involved with, list here, just to demonstrate that experience I have gained through the years, really looking into integration of renewable energy and electric vehicles. My background is power systems, but I've been working for about 15, 20 years now into the interaction between renewable energy and the grid, and also the interaction of electric vehicles with the grid. This is the project I mentioned that we are doing with colleagues in IIT GU and NIT ROURKELA. It's about development of smart microgrids, which is supported by DST UK IERI initiative. We just started a project working with a company called Bridgefault here. They are building a gigafactory in the northeast here to produce lithium-ion batteries, and they asked us to do a consultancy for them, which we started just recently. I've been involved in another project in the past on PV system performance with colleagues in India also, which was supported by EPSRC and DST. We worked on this about 10 years ago, 9 years ago, yeah. Always I try to start doing my presentation with a little bit of history, because I think understanding the history can help us see where we are heading. We can learn a lot from the history, from experiences, past experiences, and see this experience can help us project the future as well. And looking at electricity supply industry, I think many people forget that the first generators were DC generators, not AC generators. And even the first cars really were electric cars. They were not internal combustion engines, diesel or gasoline, or they were electric cars. And we had DC generators when we started. And it was until the 1890s, I think, when Tesla invented the transformer, then things start moving into AC, because they managed to step up the voltage and therefore allow them to distribute power over long distances with lower losses. But all was localized generation and supply until the 1921. They were all local generators, local suppliers, and local distribution networks. And in the UK, in England and Wales, there were 480 authorized local suppliers. And notice here, local. There was no national grid. Every local supplier has its own generators locally and distributing power within local vicinity. So they were microgrids. And then it was until 1926 when the Electricity Supply Act was set up and the Central Electricity Authority was created, which started connecting the network together, because there were many benefits in connecting different local suppliers together. And it was until the 1930s when the grid was operating as a national grid, connecting all local suppliers. So we started with microgrids, and when we moved into national grids. Obviously, when we moved into national link, there were many benefits, as I said, and this resulted in that electricity supply becomes very reliable. And we all rely on it these days. You know, our civilization really rely on electricity supply. You can probably do a similar, study on the history of electric vehicles, and you will see we moved also, even with the dates, the 19th century, so electric vehicles, the 20th century, so the internal combustion engine, and now we are thinking to go back to electric vehicles. And the reason is mainly the environment. You probably have seen these graphs before, and I don't want to mention, I think, preach again. You will probably know that climate is changing and we need to reduce CO2 emissions, greenhouse gas emissions, and the targets are 80% reduction by 2050 as compared to 1990 levels. And probably all of you would have probably been reading about the COP26, the conference, the climate change conference in Glasgow, just a couple of weeks ago, I think it was. And the debates going on there. And the reason is because there are, if you look at the pie charts here, the main contributors to greenhouse gas emissions are energy industries, electricity, transport sector, manufacturing, and residential. The rest are smaller. So if you want to have impact on the climate change or reducing greenhouse gas emissions, really you need to target these four. Manufacturing industry, we need it, but there is a lot of room you can do with residential, with transport, and with energy industry. And you can see the figure in the middle here, how these have been reduced, greenhouse gas emissions reduced by 2013 here. The target is very challenging, 2050. And if you look at the reduction, the orange one is industry. Actually, industry is doing very well, reducing their greenhouse gas emission. Grid, electricity supply is doing well also. Still, obviously, we need to do a lot more. But if you look at the transport sector, it's either the same or probably slightly increased even. So there is a lot to be done here to reduce greenhouse gas emission from the transport sector. The buildings, almost the same, despite the efficient equipment these days, the LEDs and the rest of it, but our use of energy in houses and buildings is increasing. And if you look at the CO2 emissions, the global energy-related CO2 emissions, actually they are not reducing, they are increasing. Despite reductions in greenhouse gas CO2 emissions here, but overall globally, there is an increase in CO2 emissions. I mean, obviously what I showed you here is the UK, but looking at the global picture, it's not that great. And that's why there were a lot of debate a few weeks ago in the climate change conference about countries need to commit really to reduce CO2 emissions, and they have to demonstrate clear plans to reduce this. Otherwise, we are not heading in the right direction. Now back to electricity supply. Every electricity supplier obviously wants to make money, rightly, nothing wrong with that. They want to make a profit, otherwise they cannot survive. But in order to make a profit, in order to make money, you need to provide electricity to customers where they are. And you also need to meet their demands and to deliver electricity at fair price. Otherwise, not many people will afford it or buy from you. And on top of this, technically, you have to provide reliable electricity. You have to provide good quality electricity, constant frequency, constant voltage, power quality to be also good. And these days, all of them, electricity suppliers, are required to contribute to curb climate change by using renewable energy. Increase their efficiency, achieve efficient environmental improvement in their operations. So this adds a lot to the cost, obviously, and some of these objectives are conflicting objectives. If you try to improve one, for example, if you try to improve reliability, quality of supply, or the environmental impacts, you might end up with higher costs, which you have to respect on customers. So it is a challenging balance, really, you have to do here. Looking at existing power systems, we have generation at central large power plants using fossil fuel, usually coal, nuclear, gas, oil. These days, there is some wind farms also coming in. And then this power, large power, is transmitted through transmission system, which is centrally controlled and highly automated, the transmission system. And then we have transformer to step down the voltage close to the demands, to the customers, to voltage level that can be used by the customers, whether it is primary voltage 11 or 66 kV, secondary voltage 230 or 400 volt. At the distribution level, there is limited automation and not much control really. Control is largely central. Remember, at the transmission level, there is central control and it is highly automated. So there is a lot of control there. Whilst at the distribution level, there is not much control, there is not much automation. At the load side, we have no control on the load. The customer can increase or decrease the load, whether it is with regard to size or the timing when they are switched on or off. So loads are uncontrolled, but are fairly predictable. You know, network operators, suppliers learned over the years how to predict demand and therefore plan for that. So system control has relied on power flowing from central generation to the demand. So we have directional power flow. We have central control, grid control, controlling frequency and voltage, whilst demand change, uncontrollable. And network has been designed over the year. You know, as I said, network operators learned from experience that if you calculate the house demand obviously increase or decrease during the day, during the night, but when some houses are switching on loads, other houses might not. So they use what's called after diversity maximum demand at the main distribution transformer. When you measure the demand of all houses connected to the main distribution transformer, divide this by the number of houses, the average demand, which is called ADMD, after diversity maximum demand, is about 1.5 kilowatt. So distribution networks, the rating of cables, transformers have been designed based on this. And also they have been designed that there is not much distributed generation. In fact, in the past, there were no distributed generation. Nowadays, we have many houses with PV systems. Network operators also, system operators, they do a lot of long-term forecasts. They predict what will be future demand, and then they plan for it, because building, for example, a power station or a feeder transmission line take time. So they need to ensure that in the future, in the next year, next 5 years, next 10 years, there is enough generation to supply what demand will be at the time. And then they do short-term control, which is basically voltage and frequency control. And this is central grid control, grid control. And the current control philosophy relies on controlling generation whilst demand change, because you have no control on the demand. So you control generation. Now with central power generating plants, it's not difficult to do this. You can control central power generating plants. But if you have a lot of renewable energy connected to the grid supplying power, whether they are wind turbines or PV systems, you don't have control on these. It's the sun, it's the wind that control the output. And you will see the impact of this in the next slides. So renewable energy provide many opportunities. But also they have challenges, which I'll explain in a minute. So the opportunities they provide, abundant, obviously environment friendly. Well, I said no greenhouse emissions. Some might argue, well, to build the wind turbine or to make a PV system, you obviously generate some greenhouse emissions, but they are still a lot less than fossil fuel power plants. If you have local PV generation, you don't need central generation capacity. You don't need more transmission lines. Generation is closer to loads, and there is diversity in terms of energy supply. Market development, I've put here UK. I'm sure in India, you've got a lot of development going on in PV systems. And I hear a lot of central plants, grid-connected large plants. In the UK here, we have about 21 gigawatt of wind. This was in 2018. It will be slightly more now. 13 gigawatt of onshore and about 8 gigawatt offshore, and there are many offshore wind farms being built as we speak now, actually. So this will increase. And there is 13 gigawatt solar PV. And what's important for me is 35% of this is residential. What's important for the topic of today, microgrids, 35% of the 13 gigawatt is residential and commercial rooftop. So they are close to the load. 13 gigawatt is going to move to 20 gigawatt soon, I think, in this year or next year. We'll be looking for about 20 gigawatt of PV systems and 8 gigawatt of others. So if you add these together, you will end up around 40 gigawatt of renewable energy generation capacity in the UK. Just to put this in context, the installed capacity in the UK, the electricity installed capacity in the UK is about 80 gigawatt. So almost half of the installed capacity in 2018 was from renewable energy sources. And I think we hit a few days in the summer where we had more renewable energy generation that the customer could use. So we were exceeding our expectation. In Germany, there are about 42 gigawatt PV systems, and about 90% of this is residential and commercial rooftop. Residential, commercial rooftop, 90% of 40 gigawatt. Again, Germany also had problem with too much PV generation a few years ago. So rooftop PV systems are increasing, and these are close to demand, and they are relevant to the topic today about microgrids. You'll see the graph here shows you the orange one is the rooftop PV systems, continuously increasing over the years. Looking at PV market development, PV systems these days are becoming competitive with fossil fuel generation. If you can see the brown here, I think this is brown oranges area here. This is PV residential competitiveness, and you can see the top of this orange area is when you have areas, countries with around 1,000 kilowatt hour per kilowatt generation. If you have countries with more sunshine or areas with more sunshine, obviously the cost per kilowatt generation becomes less. So you generate more kilowatt hour per kilowatt installed capacity, 2,000. And if you generate more, it becomes more competitive. 2021, we are here. You can see we are already competing with the blue one is the retail electricity cost. They have different levels of competitiveness. That's not important now. But what you see here is that the PV residential is getting into competition with the retail electricity market. So PV systems are there. They are starting to compete now. Just looking at the cost here, we moved from $100 per watt in 1970 for PV panels to now less than $1 per watt. Well, in 2013, now it is even less. So PV systems are becoming commercially viable these days, especially in areas where you have relatively high radiance. The more renewable energy we put on the grid, remember the grid was not designed to work with a lot of renewable energy sources. It was designed with centralized large power plants. So this can have impact because renewable energy generation is largely, well, you can predict to some extent, but it's largely uncontrolled and even largely, to some extent, largely unpredictable. You can do some prediction, but not a lot. So there is variability of power generated from renewable energy sources, and you lose central control. You don't have central control here as we normally have. There is potential load flow problems with regard to frequency control, voltage control, thermal limits. Even fault levels may increase, although PV systems are connected through power electronics. So the contribution to fault level is not significant. But wind turbines, many of them, they are connected directly. They are induction generators. There are some obviously using power electronics these days, which you can control fault levels. When you put a lot of renewable energy with power electronics interface connection, these power electronic devices, PV systems they don't have the inertia that synchronous generators have in conventional power plants. So overall, the grid inertia reduces, and this can cause problems with the stability of the grid also. So there is a lot of work these days looking into this, see how we can compensate for the reduction in the mass inertia of the grid. And obviously there is the cost of the connection of renewable energy to the grid, which has to be considered also. Looking now into electric vehicles, and I'm talking here about plug-in hybrid electric vehicles and battery-powered electric vehicles, which I call them electric vehicles simply. I'm not talking about hybrid electric vehicles that are self-charging, as they call them, Toyota. I'm talking about those vehicles that can be charged from the grid. Plug-in hybrid electric vehicles, they are increasing in numbers, as you can see in the graph to the left. The orange one is plug-in hybrid electric vehicle. The yellow one is battery-powered electric vehicles. But the plug-in hybrid electric vehicles, the battery is small, relatively small, 5 to 15, 20 kilowatt hour. Whilst with fully battery electric vehicles, battery is relatively large. Or saying here over 15 nowadays. You can look at the Nissan Leaf. They moved from 24 to 40 now to 62 kilowatt hours. Tesla, they are going towards the 100 kilowatt hour. So we're talking here about large batteries on wheels, really, moving around, and large range. And with development in battery technology, the range will increase, the size of the batteries will increase in the vehicle. And you need to charge these batteries. And if you look at the graph now to the right here, this gives you newly installed EV chargers by sector here. So the gray one is the fleet, then the orange one is the public chargers, and then the blue one is the private chargers, which are of interest for today's topic, microgrids. Look here, significant increase in domestic chargers. Remember I mentioned earlier, the grid was designed with after diversity maximum demand for houses being around 1.5 kilowatt. Now you are putting a charger in each house of at least a 3 kilowatt rating. There are some domestic chargers 7 kilowatt. So you are already doubling or tripling the demand in that house, which will have significant impact on the grid, as I'll show you in the next slides. Another thing to remember, I think, when you talk about electric vehicles is that electric vehicles are not really green unless they are charged from renewable energy. Because if you charge them from generator somewhere that is using coal to generate electricity, you are just shifting carbon emissions. If you charge them from green, from renewable energy, then they are green in transport. And people look at the development of EV market these days. It is exponential development. I think you can see the increase in numbers. In fact, internal combustion vehicles, this is in EU, have dropped last year, even the year before, whilst electric vehicles are increasing. The people compare this with the development of PV, how cost dropped of PV panels and this increased adoption of PVs. Same will happen with EVs when the cost of the battery drop. Grid impact of electric vehicles. There have been many studies, I think, in the last probably 10 years I've seen since I started working this year, a lot of studies coming out every day. And I think generally speaking, studies that were done on the transmission system, I think concluded that the transmission system is probably good enough. It has enough capacity probably to take up to about 10% of vehicles if they change to electric. Especially in the UK, they said there will be no problem in the transmission system. We have enough capacity, which is true. But I think the problem will happen at distribution level, especially localized area where we have high concentrations of EVs. These will cause problems to the local distribution network, and this will propagate upward. We need to remember that electric vehicles have high energy capacity. We're talking here about 40, 60, 80, 100 kilowatt hour battery in the vehicle. And if you want to charge this, it needs a lot of energy and power from the grid. We also need to remember that electric vehicles have the potential for mass deployment. There are many vehicles around. And imagine if the cost of electric vehicle becomes less than the cost of internal combustion engine vehicle. Everybody will change to electric. And if everybody changes to electric, you can imagine what can happen. Who is going to charge these? Where do you get the energy from? And also you need to remember EVs are not like renewable energy. Renewable energy is connected to a fixed place. You know where it is. Whilst with EVs, you can charge from your house one day, another day charge from work, and then you are traveling somewhere else, near supermarket or mall or whatever. So they are mobile loads. They are not, predictable loads. They are largely unpredictable, their connection to the grid, which makes it very difficult to control. And if you have few cars in the house or in the building, then this can cause more problems for the grid. And I think every car manufacturer these days, the electric vehicles manufacturers, they are looking to increasing the range of the vehicle. And increasing the range requires bigger batteries, whether it is the energy density of the battery or larger batteries. So battery sizes are increasing, and these will require charging. And the grid must provide this charge. So it is expected that an increased use of electric vehicles will cause an increase in peak demand on the grid, may cause overloads of transformers, feeders, and makes system control a lot more difficult. Looking at future power networks, this is what I think it will look like. There will be a lot of renewable energy around at different voltage levels depending on the size. But on the LV side here to the right-hand side on the 400 volt, you can see there will be also a lot of rooftop PVs, heat pumps, micro CHP maybe, lots of electric vehicle charging at the LV side. So this will results in bidirectional power flow. There is no central unidirectional flow of power from central power plants to the demand. Now it could be either way. And with bidirectional power flow, the control philosophy of the grid will have to change, because control philosophy was designed based on unidirectional. When we have bidirectional power flow, it's a new concept. So we need to rethink the whole grid, how we can maintain appropriate control with bidirectional power flow. And the best way to do this, in my view, is to try to exploit the synergies between renewable energy generation and electric vehicles. Also use storage, demand side management. So using smart grid technology, we call it, and try to mitigate the effect of bidirectional power flow in this way, rather than having to change the grid. We can't change the grid. The infrastructure is so huge. The investment there is so huge that you cannot change it. So we have to live with what we have, but we need to make it more dynamic, as I'll show you. So there is potential, I think, in the future of generation of microgrids, where we have our own generation in the house, for example, or a building, or even on the whole distribution network here, the LV side, where we have local generation that can meet our local demand. And this is very good, because then this can reduce the stress on the grid. Looking at the impact now, voltage profiles of the grid with renewable energy generation. Well, first, without renewable energy generation, this is how it is designed now. We have tap changers on transformers, and these tap changers keep the voltage at the sending end here to the left at fixed value, and then this tap changer here on the 66 to 11 kV transformer try to adjust the voltage, so push it up and adjust it fixed value. And during off-peak, when we have minimum demand on the grid, obviously current is lower and voltage drops are lower, and therefore the voltage is higher at each point on the loads here. At peak demands, we have more voltage drop and therefore the voltage drop. But the way the system has been designed is to make sure that the voltage drop at the far end of the feeder here at the end stay between the two limits, plus minus 5% here, whether it is off-peak or peak demand. Once you put distributed generator, there is potential here that the voltage at the far end, or even voltage here, this 11 kV feeder might increase above the limit because you now have supply here, some of demand. You have reduced the voltage drop in the feeder and therefore increase the voltage. Looking now on the impact of electric vehicles charging on the grid voltage, again, this is the profile without electric vehicles. And then when you put electric vehicles, it's expected that, especially at peak demand, when you have peak load here, peak demand, there will be, and you start to charge your electric vehicle, you end up with significant voltage drop in the feeder. Some time ago, 10 years ago, maybe now, we were tasked, we had a project, industry funded the project to develop a modeling tool to evaluate the impact of EVs on electrical supply infrastructure and also on the EV battery degradation. So we developed this modeling tool here. We modeled simple LV network. You can see it here at the top. LV network with feeders here supplying houses and other feeders here, main feeders, and then the transformer, 11 kV to 400 volt transformer. And then one feeder, 11 kV feeder here, and then the source here. And we could change here the type of source, whether it is urban or rural supply substation. We could change the feeder's length, type of cables, change the nominal voltage, the transformer tap here. We could do all this here. We could change the number of houses on each feeder here. We can put heat pumps, shops, whatever we wanted. So it's very really good modeling tool. And believe it or not, this was all done in Excel, not in MATLAB. So it was really good effort, I think, the team we had on the project put in this. And then we put electric vehicles also, and we could study the effect of charging of electric vehicles, whether it was a 3 kilowatt charger, 7 kilowatt charger, or a street charger, 23 kilowatt, or even fast charger, 50 kilowatt charger. And we studied also the effect of V2G. We could set the vehicle to V2G. We could change the type of vehicle. You can see here whether it is Nissan Leaf or VW or whichever. We included also renewable energy. If you look at the left bottom here, we included PV, CHP, and wind also, different targets for the UK, whether 2030 or 2050 targets. And for all these, we could produce results, as you see to the right here, bottom right, the graph for the top, the graph in the top right here is voltage profile. The one at the bottom right is the feeder current, the loading of the feeders, each of these feeders on the LV side. And then the graph to the bottom left is the transformer loading. And then here we got the data of the results, and you can see the color change. If there is any overload, the color change to red. And we even included later on the battery cycling pattern. If you look to the left here, we include how the battery is charged, whether it is charged from 3 kilowatt or 7 kilowatt charger, or how many times it charges a week. From the 3 kilowatt or 7 kilowatt, or even from the 50 kilowatt. And then we see the battery degradation effect here on this during this profile. Very interesting project it was. We used that tool to study the impact of renewable energy and electric vehicles, and you can see here the grid impact of renewables. We assumed 3 kilowatt PV per house. You can say 6 kilowatt in one house, 0 PV in another house, and so on. But it was just an assumption, really, just to see what happens to the transformer loading, end line voltage. And you can see here they exceed limit. There is potential reverse power flow, and there is potential over voltage as the on-load tap changer reaches its limit. We looked at different penetration of EVs charging, and we looked at 3 kilowatt charging. And here we looked at what we call dump charging, people coming back from work at 5, 6 o'clock in the evening, everybody plug in the car and start charging. And we concluded that for every 10% increase in houses with EVs, the demand will increase by about 15%. If it is 3 kilowatt charger. If it is 7 kilowatt charger, the demand will increase by double, 30% for every 10% increase. And the end voltage will also be affected. So uncontrolled charging can result in overloading of the transformer and voltage violation of the statutory limit. Business as usual is not an option. Here is a list of statistics I've done, collected some data about blackouts in the 1960s, 70s, and so on until now. And you can see the increase in blackouts. And some of them are really huge blackouts. They highlighted in yellow, they are hundreds of million people affected by these blackouts. And 2 of them were in India, actually. In 2001, 230 million people in India were affected by a blackout. And in 2012, 620 million. This is the biggest blackout I think I've come across in 2012, again in India. In Bangladesh, 150 million affected, and so on. So we cannot just sit and expect things the grid to run as usual. I think I mentioned about electric vehicles. They are not green unless they are charged from renewable energy. And this slide shows you this. And if we look at the graph, which is interesting, the one, the figure to the left here, which gives you the CO2 emissions due to operation of the conventional vehicles. These 2 to the left here, 2 columns to the left. These are the average European car, and this is the most efficient vehicle. These CO2 emissions from them. If you look at electric vehicles, in fact, in Germany, electric vehicles charging produce maybe slightly higher, even not the same or slightly higher CO2 emissions as compared to most efficient internal combustion vehicle. And the reason is because there are not many renewable energy sources in Germany compared to the overall demand. Obviously, they have a lot of PV, but still the demand is a lot higher than what they generate from the PV. So in Germany, electric vehicles, they are just shifting CO2 emissions from where the demand is to where the generation of power plants is. Whilst in Norway, they have a lot of hydropower plants, a lot of renewable energy. And you can see charging electric vehicles there generates significantly less CO2 emissions. France, they have a lot of nuclear, again less. UK, I think it's just managing, I think, slightly less than the normal car. So the message really is we need to have renewable energies, and we need to look into synergies between renewable energy. When is renewable energy generated? Charge there, not charge any time. Because if for example, during the day when PV generation is generating maximum, try to charge there. We need smart charging. In fact, there are many instances, for example, with wind, when you have to curtail the output if you have got too much output from the wind turbine. If you have PV, if you have electric vehicle, you can increase your charging power then. So looking at electric vehicle on their own, looking at renewable energy sources on their own, they cause problems for the grid. Combine them together, you can solve these problems. So really the solution is in them also. And all we need is to exploit the synergies between them and use smart control. We need probably to change the system control philosophy. As I mentioned before, it was based on controlling generation whilst demand change. Now we have no control on renewable generation, but we need to use smart control on the demand side management, and also use storage to help us control demand and storage while allow generation from renewable energies to vary. So we need smart dynamic control. And here is what happens if you use a smart control. The graph to the left shows you the blue one, sorry, the green one is dump charging. If everybody comes at 5, 6 o'clock and start charging, this is with 7 kilowatt. You can see there is a peak here during the peak hour. It increases the peak hour, and all the feeders, transformers will be overloaded. Whilst with the smart charging, you can reduce this peak. Charge during the day, or after midnight when there is not much demand, or during the day when there is more PV generation. And therefore, you can get rid of this peak. So it's simple, really. The solution is simple. All you need is smart control. And you can see the voltage also stays within the limit. And this is with 7 kilowatt charges, not 3 kilowatt. 30% penetration level, 7 kilowatt, and we can manage it without having to build any extra infrastructure for the grid. And one thing to note here, which is the last statement I've put, through the research we have done, we noticed that delayed charging, when you delay charging after midnight, actually it has positive effect on the battery. It reduces battery degradation, it extends battery life. So everybody is winner here. We looked at UK target for 2050 on renewables, and even with the 2050 targets, we can still use the same grid we have now. We shouldn't worry really about any problems. As I said, there could be some localized problems that that can be dealt locally, but overall, the grid can cope with 2050 renewable energies. Even better if you use the electric vehicles in what we call vehicle to grid to support the grid. You can get even better results. So if you are operating in a microgrid, and you have electric vehicle there, this can help you control your microgrid and manage your energy in a smart way, not to need the grid at all. Obviously, using the electric vehicle in V2G mode may have impact on the battery, on the degradation of the battery, because you are going to exchange energy from the battery more often. So this has to be considered and kept in mind in developing successful business models. We looked at EV and renewable energy generation profiles, and you can see the graph here. We actually use the car. Generally, the car, most people use the car, to travel to work and then commute to work and then come back home. So we use it half an hour, 1 hour, 2 hours a day, 3 hours a day, and the rest of the time, over 20 hours, is parked either at work or at home or somewhere else. So whilst it is parked doing nothing, why we don't use it to charge from renewable energy? You can see to the right here, look at the spot when there is more renewable energy generated and charge it then. So we can charge EVs from available renewable energy. And we can also use it to do other things, as I'll mention later on, to support the grid when it is not. It is a huge storage on wheels, really. Now this takes us to the microgrid. And in microgrids, we are talking here about relatively small network or energy systems where you have your own generation, or demand. It can be a house, it can be a building, neighborhood, whatever size the microgrid. It can be centralized, connected to the grid, or independent, working on its own. It depends on the control. When it is connected to the grid, you can support the grid or take from the grid power when you need it. You need dynamic control. You need to interact with the grid in a dynamic way. You need to optimize your energy use in the microgrid. If you are in a standalone mode, or we call it islanding mode, then you need to keep control of the voltage and frequency. So you need to have dynamic control, local control. And the objective, obviously, to minimize local energy consumption, to improve use of renewable energy, and improve your energy autonomy, reliability, and so on. There are several benefits from the microgrids. These are listed here, and I'll show you an example in a minute. You can read these benefits here, but the main benefit for me, really, if you look at the picture to the right here, I took this photo in Wuhan. I teach on a course there, MSc course on renewables, and the university I teach for there, when I go there, is to walk around, and I noticed this transmission line, high voltage line going between buildings. I wouldn't like to live in those flats there close to those high voltage lines. So if you have microgrids, if you have your own generation, you have energy autonomy, you don't need these high voltage lines to go through these buildings. And microgrids provide energy autonomy. All you need is really smart control. So you can self-consumption, we call it. You can use your own PV generation, but during the day, you are probably generating more than what you need. See, B here is higher than C. Whilst in the evening or in the early morning, you don't have PV generation. I'm assuming here renewable energy is only PV. So you can store this surplus of PV generation during the day and then use it in the evening. And if you have enough PV generation, you can be self-sufficient here. And there is a lot of interest now in deploying rooftop PV systems, and also a lot of interest in using battery energy storage in houses, that you can store this energy B here, the difference between B and C, you can store it and then supply A. So all you need is really to do some demand side management first, and then use energy storage. One of my colleagues, he published this paper, Pathways to Energy Autonomy. So if you are interested, you may look at it, and there are many references there about energy autonomy in microgrids. We did a project, we just finished it last year. This is the website here to the left, if you want a lot of reports on this website about this project, but I just picked one case study. We did many case studies there in that project, European project, multi-million projects it was. But I picked one study here, which was on a house. We looked into the energy autonomy of this house. It has PV, it has electric car, and different sizes. PV, I think it was 4 kilowatt PV, and it was Nissan Leaf car. And we did a lot of analysis on the PV generation, the charging profiles, and so on, and the operation, as a microgrid. And we noticed that there is potential saving in energy cost if you can create energy autonomy in this house. The house can probably save up to £522 per year. As if we use smart charging, this can improve energy autonomy and reduce CO2 emissions. And the smart charging can increase the net present value by 2K. And we also looked at using the electric vehicle to support the grid, FFR, faster frequency response, and this will bring some more income. So there are many benefits in using microgrids. Obviously, if you are standalone, not grid connected, you have to do your own control to balance voltage and frequency. If you are connected to the grid, then you can use the grid as a buffer. But you can also supply services to the grid. At the moment, there are no business models, well, very limited business models, I think, around the world for using microgrids to provide services. But I think in the future, this will become more common, that the microgrid can contribute to system balance, voltage and frequency control, and therefore get rewarded for that. Microgrids represent really a good platform to allow all users, whether you are consumer of electricity or generator of electricity, or doing both of them, to trade energy between each other or with the grid. And there could be a market, competitive market developed here. The microgrid really is at the heart of smart grid. I think many of you have heard of the smart grid. There is a lot going on this. They like this definition of the microgrid by European Technology Platform, which was set up, I think, 2006. They defined the smart grid in this way, which is basically it's intelligent integration of the grid, whether they are users or generators, how you control these in a smart way to deliver efficient, sustainable, economic, and secure supply. And to do this, you can see here the prosumer of the microgrid is at the heart of the smart grid, really. You can have full dynamic energy management in your house or building. Where you have your own generation and electric vehicle here, renewable energy here, the demands here, You have your own generator, whether micro CHP, fuel cell, PV system here, wind turbine, and then you have your thermal needs met using this microgrid, and you have connection to the grid also. Smart controller here, smart charger of the vehicle here. We did some work some years ago. One of my PhD students published this paper, also applied thermal engineering journal, Elsevier journal, simulation of energy use in building, combining both electrical and thermal. It's doable. If we want to create microgrids, we need battery energy storage. And battery energy storage can be used at grid level, or it can be used as microgrid level, which we call distributed energy storage. And microgrid level, you can use what is called stationary storage in the house. You can see here in the garage, this BMW battery on the wall here. Tesla are doing the same, Nissan, I think, and many of them are looking into using what we call second life EV battery after it finishes its use in the vehicle, instead of getting rid of it either through recycling, which is not commercially viable, as I believe at the moment. You can use these electric vehicle second life batteries as a storage for microgrids. Remember, electric vehicle batteries have high energy capacity. So if you're talking about 20, 30 kilowatt hour battery, this has to be replaced when its capacity dropped by 20%. So 30 kilowatt hour battery will still have over 24 kilowatt hour after it finishes its life in the vehicle. And this is enough to power your house for a couple of days, 2-3 days. Battery cost is coming down also, as you can see from the figures here, and this will encourage more people to put batteries in their houses. All we need is really smart control. If electric vehicles can support the microgrid in different ways, smart control, the main thing really, delaying charging, for example, or use charging from renewable energy when there is generation from renewable energy. That's help renewable energy sources, help the grid also. EVs can provide ancillary services to the grid in what we call electric vehicle for energy services. You can use your electric vehicle to drive it for 2-3 hours a day for transport, but the rest of the time when it is parked, you can use it to provide energy services for the grid. Leveling of power demand, for example, battery use, better use of energy resources available around you. And this will help you bring some reward and therefore reduce the total cost of ownership of the vehicle. And also reduce grid infrastructure, delay grid asset upgrade, for example. We published a paper also in IET how we can do this, supporting the grid without affecting the battery life, because obviously if you affect the battery, there will be penalty there. So we need to make sure that the reward you get for providing the services outweigh the cost of the degradation of the battery. You can use second life EV battery, as I mentioned before, and the battery capacity in the energy capacity in the battery is taken from vehicles after they finish their life in the vehicle is still huge and enough to power a house for a few days. Expectation, I think there is a big market there for using lithium-ion batteries, second life lithium-ion batteries. You can see Tesla here experimenting with the Powerwall, they call it. So there is potential here for integrating the energy and transport system, electric vehicles and renewable energy into the microgrid. I think all the research I've come across is pointing towards this integration, which will help really both, will help the transport sector and the energy sector. It's going to help developing sustainable transport and energy systems. Electric vehicle will see more of not only using it as a transport, but also using it as to provide energy services. The energy services are different. You may have come across these services, vehicle to home, vehicle to building, we call it electric vehicle for energy services in general. And project I did before, the website I showed you before, the European project, there are many reports on this. You can see them. These services will provide technical, economical, and environmental benefits really to the microgrid. Here is an example of microgrid market. You have different microgrids competing in a competitive market to do a balancing market, we call it. And we did techno-economic evaluation of this. One of the research students we had, and he concluded that, that there is between 4.1 to about 20% reduction in the cost of energy, depending on system configuration, if you use PV systems or energy storage. There's a lot of details in the paper here. You can look into it. But I think this work looked into the benefits of having microgrids, whether it is financial benefits or technical benefits, as you can see with regard to voltage deviation, peak demand, and reverse power flow are all reduced with microgrids by simply using smart control. Another project we had very good students who did multi-objective techno-economic environmental optimization of microgrids, whether it is within a house here or between houses here in at distribution level. And this student, I think, did very interesting work, looked into the maximum benefits for each stakeholder, because in a microgrid, you've got the microgrid owner, you've got the EV owner, the PV owner, they could be different. You've got also the grid if you are connected to the grid owner. So there are many stakeholders here. The battery is another one. The environment, you need to look after the environment also. So we need to ensure that whatever you do is really benefiting all these stakeholders, because if any one of them is not benefiting, they might not be interested. So the business model will not work. So you need to create a business model that will benefit everyone. And in this research here, we developed the maximum amount of benefit for each stakeholder. For example, energy cost saving for the user. How much maximum I can get if I use smart charging? What's the maximum if I use V2G, electric vehicle for energy service? You can see this increases. But this increase is at the cost of, for example, battery degradation. So benefit for the EV owner drops from 67 to 52. So we need to find a balance between these, and the balance is there. You can see here the grid will benefit the most in both cases. So if the grid is benefiting by 91%, they can afford to pay, for example, 40–50% of this benefit to the user, to the EV user or the energy user, the local user. And all of them will benefit the environment, whichever model you approach. So there are ways of optimizing the operation of microgrids so that all stakeholders will benefit. Again, we published a paper in Applied Energy. You can look into more details about this multi-objective optimization. And finally, the project we are doing now, supported by the British Council and the Department of Science and Technology in India. And this project, we are looking into development of control and polytronic schemes for smart microgrids. And again, we are looking to having electric vehicle. If you look at the one to the left here, we have electric vehicle, we have stationary storage and loads. We are doing demand side management on active loads. We have PV system in the lab also. And we are trying to control all of these to in what we call multi-agent control to manage the microgrid. Colleagues in India are working more on the hardware side, development of the converters and so on, chargers for the EVs. So in summary, we looked at the history and the 19th century, so the birth of electric vehicles, distributed generation. 20th century, we moved into national grid. We moved into mass production of vehicles. Unfortunately, not electric. They were all using fossil fuel, and the national grid was developed. Now, looking at this century, are we going to move into microgrids? Are we going to move into electric transport, energy autonomy? I think we are moving in that direction. How far we'll go, this depends on how these evolve. I think battery technologies, all technologies really, microgrid technology, storage, how this will evolve will determine the future. If we do nothing, there will be problems with increased deployment of renewable energy sources and EV chargers, especially on the distribution network. Microgrids will help, but will they be able to help keep reliable and affordable electricity supply and transport, as happened before? I think they will. Development of new technologies, really, renewable energy, battery storage, electric vehicle, all these developments will dictate really what the future will look like. And we need to look into the complex interaction I mentioned and try to find business models that work for all stakeholders. Because if we don't create policies that benefit all stakeholders, if we don't create win-win scenarios, the business models will not work. And in my view, I think it shouldn't be difficult to try to combine electric vehicles with renewable energy, the new technologies we have. We have a smart user. We call them prosumers these days because you can produce electricity from PV and use it also. We have smart grids or microgrids. And once we get the right policy, our governments produce right policies, business models, we can have sustainable electricity and transport systems, which is good for everyone. Thank you.
Thank you, Professor Ghanim.
Thank you.
Any question from participants' end?
Yes, may I audible now?
Yes, audible.
Yes, ma'am.
Actually, since morning I am trying, but from the rest of the audible part, like I am not able to speaking. So that is the problem. So it was a very good talk, Professor, from this end of the session. So actually, one question regarding the as the electric vehicle that you were talking, that it is of 12 volt or 8 to 12 volt for the hybrid vehicle, is it? Hello.
Sorry.
For a hybrid vehicle, can it be 8 to 12 volt kind of a battery voltage?
Well, I think generally speaking, voltage is increasing. Electric vehicles certainly is more than 12. They are talking about over 400 volt, I think, these days for electric vehicles. Plug-in hybrid, I think they will be lower than that, probably. I'm not sure about hybrid vehicles. I think it is still more than 12 volt, because if you are talking about hybrid vehicles like the Toyota vehicles, the hybrid, that they are not charged from the grid, they are self-charging. I think these have two batteries. One battery is near the engine, which is the 12-volt battery. But there is a big battery, which is the battery used to drive the vehicle in the hybrid mode. I think that one is more than a 12 volt also. But to be honest with you, I'm not sure. I haven't checked that. But I think my wife has a hybrid vehicle. I think it's more than 12 volt.
No, it is okay, because I think I have seen one i20 car where the voltage of the battery is 12 volt. Okay.
Possibly.
It is a petrol car, but the battery is 12 volt. So my question is regarding microgrid, as it is very compact. I am not working in this field for a long time. I am just coming up with a background of solid-state device and circuits, okay, from analog part. I am not an electrical engineer. I am from physics and electronics background. Now, and basically I am from microelectronics, technology and others, VLSI. Actually, the controller that you were talking about and the load in small area or in the small lab or whatever you were telling, that mostly the electronic load are below 12 volt. Okay. And the hybrid vehicle and the small equipment are also coming with LED devices. These are also kind of 12 volt. Now, the management of controller, when we are talking about, that is a kind of VLSI device where again the 12 volt is very much like 12 to lower voltage is very much is preferred. So in that case, I am trying to develop one system which will be extended to the to kind of microgrid whose battery storage is 12 volt. Okay, I am really trying to do this because of as this is really possible, because I am trying to supply the load for the electronic load specifically. So my target is to devise 12 volt like 12 volt my grid system, like my off grid system first, and if it is working properly, then it will be extended to the microgrid concept. So my question is that 12 volt, if it is 12 volt really, then I have already designed a DC bus also. Okay, DC bus where all the 12 volt like and the solar voltage, solar module, I have taken like 310 watt peak power to 350, and we have chosen because it is now available 310 minimum here. So I have taken that also. So in that case, my question is, if I am taking a system like that, so can I take a bidirectional converter from my DC bus? That is also Arnav is nicely talking about. This Professor Arnav is talking about that kind of bidirectional converter also. So really it is be feasible for that if I take one converter bidirectional, and a storage system I have taken even before the DC bus for my home delivery. Okay, home service, for the home electrical service, I have taken a primary storage, and the secondary storage I am taking from the DC bus with that kind of voltages. Now, if it is possible that you are talking about, if it is 24 volt is required, then from the DC bus, can I connect another 24 volt? Okay, so that ultimately we'll be getting, if 12 volt we can give, and 24 volt we can give. Now, my question is it feasible to give that kind of bidirectional converter 24 volt from the DC bus? Then we can proceed with for the microgrid event.
Yeah, I think the voltage level is not really a problem here. You can have whatever voltage level you want. The reason we go for high voltage level is if you are dealing with high power or high energy use, then transferring this using low voltage obviously means higher current and therefore more losses. You need bigger cables, bigger infrastructure for the microgrid. Whilst if you move to higher voltage, you can reduce this infrastructure. There are some cost savings when you use high voltage, and obviously better performance with regard to voltage profiles. For example, you've got less current for the same power, and therefore using higher voltage is brings many benefits. And this is why electric vehicles, they use high voltage. And even normal vehicles, I remember the first car we had in the family was 6 volt battery. It was an old Volkswagen Beetle. It has 6 volt battery, but all vehicles moved into 12 volt at the time. And the reason was because 6 volt battery means high current. So I remember very well, we used to replace contactors, switches more often in that vehicle, because 6 volt meant double the current to produce the same power. Whilst when moving to 12 volt is better. Large vehicles, they use 24 volt. So the higher the voltage, the better. Even when you use a 12 volt battery, what you are saying, I need to check this obviously for the hybrid, even if it is a 12 volt the battery, but actually the inverter is stepping this up to whatever level. I haven't again checked this in the Toyota, but I suspect it will be high voltage output of the inverter, which controls the motor. High voltage, I mean in the hundreds of volts, not so whilst you can use whatever voltage you want, 12 or 24 volt, it's always better to go higher in the voltage. Remember also, if you are using DC is relatively safer than AC. I think the limit we have in the lab for AC.
Yes, I am confined now in DC, with DC.
Yes, so DC has benefits also in this way. And also, obviously, you don't have, the problems we get with AC power factor or reactive power flow and so on. So it is more friendly, if you like, than AC. Another thing you need to remember also, it's not difficult these days with power electronics converters to find relatively cheap converters in the market, whether they are unidirectional or bidirectional converters, DC to DC or DC to AC converters, different types of converters. If you have a DC microgrid, you can change from one voltage level to the other. So you don't have to have the same voltage in the house, all 12 volt. You don't need this because cheap 12 volt to 30 volt, if you like, or whatever you want to change the voltage to, you can get them in the market these days. So technology is there to help you have different voltage levels in the house.
So yes, so we can provide from the output data as DC bus, then we can take several converters and to according to our need.
Yes, yeah,
Yes.
absolutely.
Okay. Thank you.
Thank you.
Any more question?
Hello, sir. Hello.
Hello.
Yes, yes, continue.
Yes, sir. Thank you, sir, for your nice talk about electric vehicle and microgrid. So, just I want to know, sir, what is the recent challenge in electric vehicle? So, can you elaborate something about the recent challenge actually in electric vehicle?
Are you asking about the challenge in electric vehicle, for example, manufacture, or electric vehicle impact on the grid? Or
Impact
both?
on the grid. Impact on the grid.
Yeah. Well, I think I wouldn't say only impact. I think electric vehicles, we need to look at them both ways, impact and also opportunities. Whilst they can cause a lot of negative impacts on the grid, for example, with regard to, for example, loading, extra loading on the grid. As I said, the house was designed for after diversity maximum demand of 1.5 kilowatt. If you put 3 kilowatt charger, you have straight away put twice the original demand of the house. You increase it by twice. So this can cause, if it is one house, there is no problem because the grid has small capacity usually. But if many houses can do this, have chargers, then this can cause a problem. At the moment, electric vehicles are relatively more expensive than normal vehicles, conventional vehicles. So not many people can afford to buy electric vehicles. But as the price comes down, and I show you the figures about batteries, almost half of the cost of the electric vehicle is the battery. Now, if battery costs are coming down, I think I'm saying half, this was probably 4 or 5 years ago. Now they are less than half the cost, and they will continue to come down. So with the advance in battery technology and the reduction in the cost, electric vehicle cost will come down. And as the cost come down, people will be tempted to buy electric vehicles more than conventional vehicles. When I did presentations a few years ago, energy prices were down, oil prices were down. So people are saying, oh, no, we are not going to run into problems with conventional vehicles. You know, it will be cheap to run them. No, I think we have witnessed here in the UK this year, petrol prices rose probably by about 30% from 1.1 or so to 1.5 now for petrol to buy it per liter. 1.5 pound, not dollar, per liter. So they are becoming a lot more expensive to run. Yes, they are cheaper to buy, but a lot more expensive to run. Whilst electric vehicles are a bit more expensive to buy, but they are a lot cheaper to run. So I think once this balance tilt towards electric vehicle, more people will have electric vehicle, more people will have chargers at home, more chargers on the street to meet the demand, and this will increase the demand on the grid. The grid will not be able to cope, as I mentioned in the slides, depending on if it is dump charging, if you have localized 10% even of the vehicle change to electric in a localized area, this can cause a problem to the grid. You can solve the problem by using smart charge control. So there will be issues. That's overloading of the feeders, the transformers, as I mentioned you in the slides. Also, there could be reduction in the voltage, especially at the far end of the reader, because of the increase in the loading of the feeders. Voltage drop will increase, and therefore the voltage, especially at the far end of the feeder, will drop below the statutory limit. So there are many impacts on the grid. And obviously makes if you are looking in a microgrid, especially if it is a small microgrid, the impact will be higher because the consumption of the power consumption of the electric vehicle during charging is probably more than the consumption of all your house. So you can imagine when you do welding in the house, you get light flicker or affect the operation of your fridge or freezer. The same thing with electric vehicle. When you switch it on, the voltage will drop. All the appliances in the house will, on the microgrid will drop. The voltage will drop. So there could be significant impacts, and this depends on the size of the charger and also the size of the generation and demand in the house or the microgrid. Hope this answer your question.
Yeah. Yes. Thank you, sir. Thank you.
Thank you.
Any more queries?
Prof. Ghanim, I have a query.
Okay.
The rate at which we are moving towards electric vehicle, since at the same rate we will not move towards this demand side management and smart grid concept, then what will happen to our grid? Means if will same rate will move, then there may be balance, but if will not move in the same rate, then what will happen to our grid? And for that, is there any policy from government side is required, or what is the solution?
Yeah, I think if we do nothing, it depends how how electric vehicles will evolve. In the UK, I think with the pickup, I showed you some of the slides. In Europe and UK, electric vehicles are increasing in numbers. I used to walk outside on the streets here in Newcastle. Every probably day I will see few electric vehicles now. I walk these days, every minute I see probably electric vehicle coming this way or that way. So number of vehicles is increasing. Every government, I believe in India the same also, there are policies to install more chargers, because one of the obstacles to uptake of electric vehicles, people are afraid they get abandoned and there are no chargers everywhere to charge their vehicles, like with garages, for fuel, petrol or gasoline. There are many of them. So governments are building more chargers. In fact, they are giving incentives to people to put chargers in their houses. So more people are putting chargers in houses, more on-street chargers. Now, if it is on-street charger or fast charger in a 50 kilowatts somewhere, I think this will be installed by liaising with the supplier, the grid operator, to find a strong point to connect that one. So that will not likely to cause a problem. Those that will likely to cause problems are in houses, because they are not, you can do it without informing the network operator. Suddenly the network operator will see an increase in demand in that area. And these will cause problems. I suspect if we do nothing, we will have more cut off, more blackouts, local blackouts, maybe not central, central blackouts, but local. I think network operators are trying to speed up development, if you like, as more electric vehicles are coming. The reason we did the project I mentioned, the modeling tool, because network operators and companies who are installing electric vehicles, they want to see the impact. So we analyzed the impacts 10, 15 years ago, and since then they are working on trying to mitigate these impacts, designing the network to try to mitigate these impacts. Governments, I think they have policies this is why they are encouraging microgrids, for example, because they know solution to this could be, instead of building more stronger electricity grid, more towers, high voltage towers, encourage people to have microgrid, encourage people to have PV systems on their roof, encourage people to use a smart control, encourage people to use their electric vehicle to support the grid and support the microgrid. So all these, I think the technologies will move. If we don't do any of these, we will be in serious trouble. I think the more obviously we leave it delay it, the more serious is the problem. The new technologies will help us overcome these problems. And I think they are developing, evolving hand in hand, if you like, as the problem, the potential problem increasing. At the same time, I think governments and technology is moving also. So they are preventing the problems from occurring until now. And hopefully this will continue in the future also.
Another thing is nowadays we are in our existing grid, but nowadays renewable already means entered into our power system. Then if more EV will come into our power system, then at that time what will happen? Our generation is unknown, our demand is unknown. So if we don't know how much our generation may be more. So at that time, so with our existing protection system, so whether our existing grid we can operate or what will happen?
Well, I think already problems are occurring due to an increased penetration of renewable energy. Electric vehicle, they started, I think renewable energy started before electric vehicle. So we saw some problems, I think, before from an increased penetration of renewable energy. We will see more problems, I think, of electric vehicles. But as I said, at the same time, I think as more renewable energy is being connected to the grid, we are learning more from past experience. For example, in Germany, when they had a lot of rooftop PV systems, and I think probably about 5 years ago, there were no problems. But as the number of PV systems increased, and during a sunny day in summer, there was more generation than the demand, and the grid was shut down for a short time. And the lesson they learned is that they have to have control on the inverters of PV system to be able to curtail. I think they didn't shut down, they curtailed the PV system. They shut down PV systems. But the lesson was learned that every inverter nowadays must have a control signal from the supplier, the grid operator control room. If for example, the generation become more than demand and there is a problem for the grid, all the inverters automatically, they have to curtail their output. So I think as we are moving on, we are learning, and the good thing is technology is helping us. Technology is moving a lot faster than power systems. I do other webinars, talks, I think, when I talk about technology also. Imagine, mobile phones, how they moved. Think of the computer technology, power, memory. We have a lot of power in our hands now. That power systems, they are very conservative. They are very slow in adapting new technology. And I think understandably, they have good reasons for that. I was talking maybe 25 years ago, I think, when I started here in Newcastle, with the control engineer at the local distribution network about power quality. And he said, no, we don't have problem with power quality. We don't want to do any research in this area. And a few years later, they came back to me and can we do some work on this? So I think power system engineers are very conservative. But there is a lot of good technology there to implement in power systems to make it more smart, if you like. And I think engineers, they realize this, governments, they realize this, and everybody is now trying to implement the new technologies, whether it is computer power, smartness, networking, mobile communication, bidirectional communication. Smart grid relies on communication links. So technology will help us.
Thank you very much for giving a nice talk. Actually, this is the need of the hour, this type of talk. Actually.
Thank you. I think there is somebody, there is a hand up. I don't know if you want to.
Yes, yes, sir. So actually, I have a query. In future power generations pertaining to random solar penetrations or random renewable penetrations, stochastics renewable penetrations, there are and asynchronous generation penetrations are going to be increasing day by day. So if and also electric vehicles penetrations is also going to be increasing day by day. So pertaining to this asynchronous generation, more penetration, if we give more focus on in addition to battery energy storage system, pumped storage hydro units, if we decentralize the local control centers, and in each unit, if you insist more on pumped storage hydro units, then despite of giving the balance between demand and this demand and supply, they will also have, then that means they will also compensate for mismatch in inertia due to penetrations of more asynchronous generations. So I think the pumped storage hydro units are given more importance to be placed in each control center to counteract this mismatch in inertia due to this random penetrations in a future power network. Then can it be a viable solution to meet the inertia demand, inertia mismatch?
Yeah, I think that's a very good point you raised. There is a lot of research going on, I think, trying to find a solution to this, because obviously the more PV systems connected with power electronics, more wind turbines coming now with power electronics, so the energy on the system is reducing, and this has impact on the stability of the system. There are limited pump storage units there. There are limited rotating machines there, generators. So you are absolutely right. Again, if we do nothing, there could be a problem with the system inertia in the future. And one area that I have come across that people are working on, I haven't worked myself on this, but I've come across many research projects here in the UK, where people are working on creating virtual inertia. So you control your PV system inverter, you control your power electronics in the wind turbine in order to generate what they call virtual inertia. So the power system, actually, it's not mechanical, as we know it, inertia, it is electrical inertia. For example, battery storage also, electric vehicle can provide inertia. So I think the source of inertia is shifting from having rotating machines into having virtual inertia provided by batteries or power electronics control. And the trick is the technology. Again, technology will help us do this. So whilst inertia can be a big problem if you do nothing, with technology, we can create system inertia. And I think Professor, she asked at the beginning about the moving into DC. There are a lot of work also going into trying to create DC microgrids rather than AC. And if you move into DC, you don't have problem of stability there, like with AC, the rotating machine and stability as we know it. So technology is going to help us overcome the problem of inertia in power systems.
Yes. Thank you. Thank you.
Thank you. Thank you.
Okay, we'll wind up here. So thank you very much, Professor Ghanim, for a very impressive talk. Thank you.
Thank you very much. It's been a pleasure.
Yes, sir, for your talk as well as good discussion session was there. So thank you.
Thank you very much.
Yes, thank you.
Thanks.
May we collaborate with that UK, IRD and others with ROURKELA and the university, that mostly, although we are trying to develop electronic load to support the electronic load. So the things that you are talking about losses, as we are from device, so we'll be trying to model in a better way so that we can exploit all those. And the switching frequency now, gallium nitride and other frequency devices are coming. So I think the high-speed switching is possible nowadays. So with the advancement of technology, maybe the smart converter and the MPPT charge controller also can be possible with like neural network and other like machines are coming. So I think it will be better if we can you can suggest something so that we can collaborate with that.
Yeah, I think there is a lot of potential there. We only need to talk to each other and keep discussing.
Yes, sir. We are very much interested. Okay.
Yeah. Thanks.
Thank you.
Thank you.
Thank you. Have a nice day.
Thank you, Prof. Ghanim.
Thank you, sir. Bye, sir.
Bye-bye.
Bye-bye.
Bye.
Thank you so much. Bye bye.
Bye. Thanks.
Thank you very much.